So as I said in the previous slide, to say that the limit of f exists as x tends to c, that means that the limit exists along all paths approaching c, and this has a couple of implications. So first off, showing that a limit actually exists is actually really hard because you almost have to check infinitely many possible paths coming in towards c, right? Now there's ways around that and other ways to argue, but that's really something you do in a class like Math 412 or something, an analysis class. But if we want to show that the limit doesn't exist, that's not so bad. That just means that we need to find at least two different paths which yield different limiting values. So if I come in towards C, in one direction and I get one value, and if I come in along some other path and get some other value, then I know that there's no way that the limit can exist and there's no way that the function can be continuous at that point. So that's usually what we try to do. So when we're looking at the limit as, say, let's just do 2 dimensions here, and we'll go back to using the xy as our coordinates. So the limit as xy tends to the origin of some function. This is the thing that we're most often going to be testing. And so what we'll do is we'll take a path, so a coordinate is a parameterized path. So let's say CT is, and then we'll have like an x coordinate and a y coordinate. And so then when we want to see as this function is tending to 0, then we can replace the original setup with something which is simpler, which is just the limit as t goes to 0 of f of c of t. Okay, so now this is assuming that c has been chosen so that it passes through the origin at time 0. So I need that there. Okay, so then it's just a question of picking a nice c. A nice path. Okay, so that's what we'll do. So let's look at some examples. So suppose we consider the function f of xy is equal to x squared minus y squared over x squared plus y squared, and we'll look at the origin 0, 0. Okay, so suppose we want to look as we come in towards the origin along the x-axis. So if we do along the x-axis, then we could use a parameterized path that looks like t comma 0, because on the x-axis that's where the value of y is equal to 0. So then we look at the limit as t goes to 0 of this path. So this is going to be f of t comma 0 because we're using this parameterization. And so that means that we substitute into our formula. We're setting x equal t, and we're setting y equals 0 in our path, because that's the parameterization we're following. So this is going to be t squared minus 0 squared over t squared plus 0 squared, which simplifies to t squared over t squared, which for any value of t is just going to be equal to 1. So the limit as t goes to 0 of the constant function 1 is just 1. So that's telling us that we have a limiting value of 1 as we come in along the x-axis. Now if we come in along the y-axis, then we could take some other path. So this is going to be 0t, that makes sense. And so this is going to be the limit as t goes to 0 of f of, and now this time we're setting x equal to 0 and y equal to t because we're coming in on the y-axis. And so when we substitute that into our formula, then we have 0 minus t squared over 0 plus t squared, which simplifies to now -1. And so it takes value -1 everywhere, so in particular the limiting value is also -1. So we get different. We got different limiting values along different paths, so we can conclude immediately that the limit does not exist. And if you were working a homework problem, you could stop right there and call it done. However, since this is a lecture, discussion, whatever, and we want to investigate like just what kind of crazy business is really going on, let's do a little bit more spelunking. So suppose we come in along some straight line of slope m. Okay, so here we could take our path to be, so this equation says y equals mx. So that's saying the second coordinate is m times the first coordinate. So if the first coordinate is t and the second coordinate is m times the first coordinate, it's going to be mt. So we take the limit as t goes to 0 of f of t mt. And what is m? It's just some number that we've chosen to be our slope. I just want to know, in general, what happens if I come in along a line of slope m. And so then we've got t squared minus mt squared. With parentheses. And we have t squared plus mt squared. And so now I can factor a t squared out of the top and the bottom of this expression. And I get 1 minus m squared over 1 plus m squared. And there's no t's in that, so that's a constant value. And so that's going to converge to 1 minus m squared over 1 plus m squared. And if you poke around with this for a little bit, you'll see that this expression takes some value in the interval from -1 to 1, depending on how you choose m. So in other words, so the upshot of this is that we can choose our slope m so that the limiting value as we come in is anything in this interval. Which is crazy, right? That's absolutely crazy. How can this be possible? Well, let's take a look at the graph of this function to find out. Okay, so here's what we have. Here's I've plotted it from 2 different directions so you can see what's going on. And you can see that as we come in along the, let me grab some red here. As we come in along the x-axis across the top here, coming in, actually that didn't show up at all. Maybe green? Slightly better. Okay, so as we come in from the positive side or from the negative side along the x-axis, we're walking along the top of that ridge there. So that's coming in this way or this way here. That entire line across the top is suspended at vertical height 1. Meanwhile, if we come in along from the positive y-axis or from the negative y-axis, we're heading towards -1. So that's coming in along the bottom of this valley here or here. And if we choose some height in between, then there's a line that comes in that, so these lines here are all at different heights. But those are all like horizontal lines approaching the origin, and depending on which direction I come in from, I can have a different limiting value. And you can see there's like this big nasty spot right here in the middle where it looks like there's a split. There's actually no gap there. That's just Mathematica having a heart attack trying to graph a function that's this ugly.